So
Just let me know whenever you'd like me to start.
okay, so I'm going to introduce you real quickly, and then you can go ahead and start.
Bert.
Okay, so today we have our presenter, Gus Tolley, a hydrogeologist, today presenting the ghosts of California's groundwater. And so I'm going to go ahead and pass it along to Gus to present.
Thank you, Sydney. So I was asked to give a talk, and I know this is a Sierra Nevada Alliance, and I am a PhD from UC Davis. I did my undergrad at UC Santa Barbara in geology, and then switched over to hydrology and went to New Mexico and worked there, and then finished at UC Davis. And I don't explicitly do any research specifically in the Sierra Nevada, but what I thought would be interesting is give you guys a general overview of some groundwater history and where we're currently at and where we're heading in California as far as our SGMA efforts go. And I'll get into that later if you've never heard of SGMA before. But I think this might be just interesting from a general information perspective, because this is honestly one of the biggest experiments that California has performed in quite some time, and you'll see why. There we go. Okay. So I like to start off general groundwater talks with this little cartoon, because this is pretty much most people's understanding of where they get their water from. They know that there's precip up in the mountains somewhere, and they can turn on their taps and get the water, but they don't really have any information about that middle part. So how it goes from precipitation into their houses. And so hopefully I'll fill in a little bit of that information in that middle box that most of you are probably missing, which is completely understandable because you're not hydrogeologists, and so there's no reason why you shouldn't really know about it. So if we look at our amount of storage capacity, both in groundwater and surface water, our groundwater storage capacity is significantly larger than surface water storage. So a lot of times you'll hear, as far as water resiliency, people saying, oh, we need to build more dams and store more water. Well, unfortunately, that's not a good option moving forward, partly because surface water storage is incredibly expensive. The other reason is that there's just physically no really good opportunities to build them. All the good sites have already been taken. And so what this figure is showing you is the reservoir capacity for surface water in California. And it's about 50 million acre feet, give or take, which is quite a bit. And I'll get into what an acre foot is in just a second here. But if we look at our groundwater basin capacity, and this is a really, really cool infographic from a group called Water in the West at Stanford University. And unfortunately, we don't know exactly because the groundwater system is a little nebulous. We can't directly observe it. And so there's estimates of anywhere between 1.3 billion to 850 million acre feet, which is approximately about 20 times larger on average groundwater storage capacity than surface water storage. So the capacity to store groundwater is much, much greater than surface water storage. And so a million acre feet, so an acre foot is essentially the size of a football field covered with 1 foot of water. One acre is essentially 1 acre with 1 foot of water, and 1 acre is about the size of a football field, give or take. So we're talking about huge quantities of water here. A million acre feet is 326 billion gallons of water. And so 1 million acre feet would cover the entire Central Valley with approximately 1 inch of water. And so I want you to, if you take home one thing from this talk, just know that measuring water in California using gallons as your unit is a terrible way of going about it, because it can make something that sounds like a lot, like a million gallons of water, is actually a relatively small amount in the grand scheme of things. And so if we look at where we're getting our water supply from in California, typically about 40% of demand across the state is met by groundwater. And so this varies. This is a long-term average. So in wetter years, it might be a little bit less, and in drier years, it can be up to 70%. And so there's a lot of communities that nearly rely completely on groundwater. And a lot of these are along the coast, and this is because they don't have a whole lot of precipitation there. And so they have to rely on these groundwater resources. And this is a critical resource for many farmers in the Central Valley and the Central Coast. And if you look at across the state, about 85% of Californians rely on groundwater for either some or all of their water supply. So it's a very vital resource for people that live in California. And so if we sort of look in the past at how we've dealt with groundwater, we haven't formally regulated it for over 160 years. So this is just showing you a timeline of where we've come so far. So in 1850, California became a state. It was in 1914 that the first official surface water regulation began. And so this was primarily what's called a prior appropriation right. So a lot of this was for mining, and it's a first in time, first priority right. And so in 1969, we went from 1914 to 1969. The next major regulations of groundwater was this Port of Cologne Act. And so this was mostly water quality, because Port of Cologne covered both surface water and groundwater. And so it wasn't until 2014, or 100 years after we had our surface water regulation, that we actually started officially regulating groundwater on a statewide uniform basis. So we have a lot of history of sort of looking the other way when it comes to groundwater. And so before Sigma, or pre-2014, this is pretty much what groundwater management looked like. It was people fighting over something, and they would go to the courts. And largely, if nobody was being affected or nobody was injuring their neighbor, then people were happy to look the other way, and groundwater conditions could deteriorate as long as nobody in the valley was really being affected. And so these adjudications, most of them are in Southern California. And so this is for two reasons. One is that they're very long and very expensive. And so the water needs to be relatively scarce for people to want to spend the money to actually go through with one of these adjudications. Like I said, on average, I think adjudications are around a 10 to 20 year process. So it's incredibly expensive. So most of these are going to be down in Southern California, where there's less precipitation and greater population. And so therefore, water's a bit more scarce. And so if we look at, there's actually one adjudication in Northern California, which is the Scott Valley, which is where I did my PhD research. So it's near and dear to my heart. And this is just an example that I like to show people, in that a lot of the times these adjudications are, based on lawyers that were drawing lines and not hydrogeologists. And so what you're seeing in this figure is the orange area is the hydrogeologic groundwater basin. So this is the alluvial aquifer. And the blue area is the actual adjudicated portion of the basin. And so these adjudicated boundaries don't always coincide with hydrogeologic boundaries. So even if a basin is adjudicated or partially adjudicated, there can be issues where you have these imaginary arbitrary lines that are drawn in the aquifer that don't have a physical barrier. And so on one side of that blue area, you can pump as much groundwater as you want and nobody can stop you. And on the right, and within that blue area, there are rules. And so we're talking, you can move a well by 10 to 15 feet and not be regulated within that adjudication. So that creates its own issues. And I'm not going to give you, any other equations except for this simple one, because it's very relatable. So water budgets are basically governed by the simple mass balance equation. And you can think of this just like, so groundwater acts just like money in your checking account or your savings account. So what comes in minus what goes out is your change in storage, or you can think of storage as your account balance. So if you're putting more money into savings than you're taking out, your account balance is going to grow. Same thing, if you put more water into the aquifer than you're taking out, then your water levels will come up. Vice versa is also true. If you're taking more out than you're putting in, then your water levels are going to decrease, or your bank account is going to decrease. So it's relatively simple, and the devil's really in the details as far as how we partition these inputs. So these can be, precipitation or natural recharge. There can be recharge from irrigation, mountain front recharge, which is very difficult to quantify, and so on and so forth. And then we also have our different outputs. So this can be evapotranspiration, or how much water is being used by plants, or also just directly evaporating off the surface. How much is running off? Is there groundwater pumping? Is there groundwater surface water interactions? So on and so forth. And so if you, just like if you are spending more money than you're bringing in, then your account balance is going to go down. And what this plot is showing is from 1922 to 2009. So this is a little outdated, but it's one of the better infographics. The trend is essentially the same. Where this is showing different regions in California that have had different change in storage. So as that line is going down, your outputs are greater than your inputs, and that's what we call groundwater overdraft. And so you can see that for most of the Central Valley, we're actually doing okay, or in the Sacramento Valley even, we increased our groundwater storage. And this is because depending on your irrigation schemes, including agriculture in an area, can actually increase recharge, because if you have inefficient irrigation, is efficient groundwater recharge. But what I want to focus on is this line right here. So this dark blue line is sort of the total for the Central Valley. And this orange line here is for the Tulare Basin, which is the southern part of the Central Valley. And so you can see since about 1922 to the present, we've had this consistent decrease in groundwater levels. Right here is when the Central Valley project started coming online. So there was a greater amount of surface water deliveries, but then irrigated acreage expanded, and those gains were quickly lost. And you can see there's a few blips here where there's some wet years, but in general, this trend has been moving downward. And so we've been taking more water out than we've been putting back in. And so this cumulative overdraft, if you look at it, remember, a million acre feet would cover about 1 inch of water for the entire Central Valley. So if you look at these numbers, the cumulative overdraft would be about 10 feet of water in the Central Valley. And so that doesn't mean that water levels have dropped by 10 feet. It means that water levels have dropped by greater than 10 feet, because the porosity in the aquifer, there's solids in there. So 1 foot of water decline in, say, in a lake is different than 1 foot of water decline in an aquifer. It's usually about a 1 to 10, 1 to 20 relationship. So that means that water levels have dropped by dozens to tens of feet. And this is also what we see. This is a plot, again, from Water in the West in Stanford. So from 2004 to 2014, and 2014 was right in the middle of a very significant drought, the most significant that we've had in modern history. And this plot is showing you where these decreases of water and what the magnitudes are. So lots of red areas, which are decreases of 10 feet or more. And you can see down here, so a lot of these would actually be probably on the order of dozens to hundreds of feet. So the consequences of groundwater overdraft and or mismanagement can be very severe and long lasting. And so there's these, and I'm going to get into exactly how Sigma addresses this, but these are the things that Sigma is working towards. So the first is these severe economic and social costs. So on the left is a photo from the LA Times during the drought, where people's wells went dry and they had to start trucking water in. And so you can imagine, if you don't have access to clean drinking water, how stressful that can be and how much extra money that costs to truck this water in. And on the right is a plot from a paper that came out in 2015 that showed the increased economic costs of lowering these groundwater tables, groundwater levels as far as they have. And note that these values are in thousands of dollars. So this is not $100,000. This is $100 million increase in pumping costs for some of these areas. So this is a significant economic cost that we're dealing with. And so another issue that can happen if there's overdraft is land subsidence, and maybe you've heard about this. And this photo on the left here is one of the most famous photos in groundwater hydrology. And what it's showing you is where the land surface would have been without this groundwater overdraft. So in 1925, the land surface would have been way up here at the top of this phone pole, and it's steadily dropped. And this is also recreated more recently by Michelle Sneed. And so she's showing it's not as dramatic as it was before, but it's still significant. And so what land subsidence does is the real effect is on engineered structures on the surface. So there's some estimates that the California aqueduct, which moves water from the north down south towards LA, has lost about 30% of its conveyance capacity. So 1/3 of the amount of water that it used to be able to move, it can't anymore, because you've slowly lowered the elevation in some areas, and these canals rely on a very, very shallow gradient. So we're talking maybe 1 foot per mile. And so if you have 2 to 3 feet of substance right in the middle of that, you now have a lake where your canal used to be. And anything else that's also an engineered structure that can be affected by differential land movement. So for example, the high-speed rail, bridges, those are all susceptible to land subsidence. Another issue that comes up from groundwater overdraft can be water quality impacts. So on the left here is showing what we call seawater intrusion. So if you're located near the coast, fresh water that's mounting near the surface is pushing that seawater away and keeping keeping that salty water from intruding into the fresh water. But what happens is, as a result of something called this Geibin-Hertzberg principle, for every foot of fresh water that you pump, you're going to increase your seawater intrusion by about 40 feet. So there's a very linear but very strong movement of fresh water, or excuse me, salt water into freshwater areas as you start pumping near the coast. And so this can, essentially take out a lot of wells from production because those wells are now salty and we can't use them for either drinking water or irrigation. And the figure on the right is showing a new paper that's currently in review from a friend of mine at UC Davis, where if you're familiar with closed basins, so for example, the Owens Valley or lots of basins in the Basin and Range complex, where you don't have a natural outlet for the surface water, the water can collect and evaporate, but all the solids and all the salts that are in the water and dissolved in the water from the rocks have no exit. So those salts just keep accumulating and that water gets saltier and saltier and saltier. And so you can do this artificially by pumping so much groundwater that you now don't have any outlet for the groundwater. You create this large, what we call a cone of depression. And so all the groundwater is now flowing back into the basin. There's no outlet for those salts. And eventually that water is just going to keep getting saltier and saltier and saltier. So this is a very scary proposition that is currently happening in the southern part of the Central Valley. And so another issue with groundwater overdraft, or even just groundwater pumping, it doesn't necessarily have to be groundwater overdraft, is stream flow depletion. And so these are just schematics that show you what happens when you pump a well. On the left-hand side are 3 different wells that are located at various distances. So well C is located the farthest from the river, and well A is located closer by. So you see there's a much more pronounced effect that's of shorter duration, but much sharper magnitude. And the effects from well C are spread out a little bit more, but not quite as acute in one area. And essentially what happens is as you're pumping, you can deplete the amount of surface water that's in there. You can do this by either decreasing the groundwater discharge or the amount of groundwater that's discharging to surface water, or by inducing leakage from the stream itself. So those are 2 different ways that stream flow depletion can happen. And so in 2014, California passed the Sustainable Groundwater Management Act. So in the middle of one of the worst droughts that we've experienced, we had a significant policy change, which is pretty remarkable. And so what the Sustainable Groundwater Management Act, or SGMA, does is this is essentially a stop the bleeding type approach. So what we're not going to do is be able to get back to where we were pre-development. That's just not going to happen. What we can do is stabilize the patient. So this is going to prevent conditions from getting any worse than they currently are. And under SGMA, it's January 1st, 2015. So anything that you did prior to January 1st, 2015, we have to live with, but you can't get any worse from there. So it's definitely a compromise, but it's better than nothing. And so January 1st, 2015 is where this demarcation line is. And so SGMA applies to all of the 515 groundwater basins in California. And so most of these are going to be low priority basins. And so DWR, through their basin prioritization, they've identified 69 medium priority basins and 26 high priority basins. And so they've basically given a numerical value based on different criteria. So one of them would be population. If you have a large population in the area, they're going to be concerned. Second is number of wells. If you have a lot of irrigated acreage, your dependence on groundwater, so on and so forth. So what SGMA does is it's one of the things, so we didn't have any formal groundwater regulation for 160 years, but what that allowed us to do is to gain as much information from other people that have been doing this. So even though we're a little bit late to the table, we were able to learn from a lot of other entities that have tried to do this over the years. And so I believe that they've actually gotten the approach right, or at least as right as we can. And so what it doesn't do is it doesn't define sustainability. So that's very difficult to do. What it does do is it defines unsustainability. And so it does this by identifying these 6 undesirable results, or what we like to call these 6 sigma sins. And so these are lowering of groundwater levels, reduction of storage, seawater intrusion, and degraded water quality. So a lot of these are somewhat similar, but seawater intrusion is a specific subset of degraded water quality. And then land subsidence, like I showed you before, and then surface water depletions. And so these have to be significant and unreasonable. So it's not that you have lowered groundwater levels, is do you have these chronic lowering of groundwater levels where they haven't leveled off? Because we understand that this groundwater resource is a buffer against droughts. And it's a resource that we should be able to take advantage of during dry periods. But at the same time, we need to make sure that we're not over exploiting this resource, and so that it will be available for years and years to come. So the way that SGMA works in a nutshell is groundwater sustainability agencies within a basin. And these can be sort of any agency that is like a special act district, a flood control district, irrigation district, even counties. These get formed so you can have multiple GSAs within a basin. You can have a single GSA, and then they will form a groundwater sustainability plan. And again, SGMA is very flexible. You can have multiple GSAs that form multiple groundwater sustainability plans where they coordinate with each other. You can have multiple GSAs that form a single GSP. You can have one GSA that has multiple GSPs within a basin. Again, it's as long as the entire basin is covered by some combination of GSAs and GSPs, then they're happy. And there's this target goal of 2042 that sustainability has to be reached. And so we essentially, and so this is what we call local control with a state backstop. So the local control aspect is really important because groundwater hasn't been regulated in, or I should say officially regulated on a statewide basis. Nobody was going to go for the state coming in and telling everyone what to do. And it also doesn't make sense because there's a lot of issues that are very specific to localities. And so having the locals be in control of these plans allows them to be developed in such a way that you can get consensus a little bit easier. Now, the state backstop comes in because you have to have some controls saying, we can't just let people say, yeah, we're fine with, 100 feet of subsidence or, whatever it is. So there has to be some limits, but for the most part, the locals are the ones that are taking control of this. And so DWR has used a bit of a carrot and a stick approach, where the carrot is they've provided a lot of money and a lot of grant opportunity, especially for areas that are disadvantaged. And so to develop these plans, and the stick approach is they've essentially said, if you don't make a groundwater sustainability plan, we will come in and we will limit the amount of pumping because that's the easiest way for them to do it, and it's the cheapest, and it doesn't take into account any of the local nuances that they would have to learn. And so they've made this very clear. And so now we go into so we have these impacts and we've passed SGMA. So now how does a basin define sustainability or unsustainability? And so this is part of developing this GSP. And so let's look at examples. So we're going to look at something that's relatively easy, which are these lowering of groundwater levels. And so part of the GSPs is developing what are called sustainable management criteria. And these really consist of 2 parts. So the first part is you need to have a measurable objective. You need something that you can actually physically go out and collect data on. These can't be esoteric, oh, we want, our groundwater levels to be at a reasonable place where we can, there's not gonna be any impacts. No, you have to say our measurable objective is groundwater elevations should be around X amount of feet above sea level. And the second part is a minimum threshold. And so this is a level that you don't want to drop below. And so typically these would be levels that were at, January 1st, 2015, where you can't get any worse from there. And so this is what you're essentially saying, this is our worst case scenario is we want to stay away from this. And so in between you can have management triggers where if you start approaching this minimum threshold, then you start implementing things like, okay, if we get to, and again, for lowering groundwater levels, it's relatively easy to wrap your head around. We can say, for example, we want our groundwater elevations to be at 100 feet. Our minimum threshold is 50 feet. And maybe when we start getting to 80 feet, we start thinking about cutting back on pumping, or we implement some other projects, something to prevent us from reaching this minimum threshold. So where are we currently at in the signal process? And so this is that same timeline that I showed you before, and I've extended it just a little bit. And so we're currently here where that blue arrow is, which is about 18 months before all the GSPs have been submitted. Earlier this year, and I'll get into it a little bit later, but the critically overdrafted basins, their GSPs were due 2 years before because they were on accelerated timeline because they're critically overdrafted. So 2022 is when all the GSPs have to be submitted, and 2042 is when all these basins are required to achieve sustainability. So you have 20 years from submitting your plan to actually achieving the end goals of that plan. And I like to show this timeline because it really shows you that in a relatively short amount of time compared to where we've been. So this black area right here is sort of mostly before groundwater development in California began. And this is because we just didn't have the technology to pump a significant amount of water from the basin. But in around the 1920s and 1930s, with the invention of the centrifugal pump, we could significantly extract, or we can extract significant amounts of water from the Central Valley, and that led to this boom in agriculture. And so this brown area you can see or this brown length is much greater than this green length. So we're really trying to undo a lot of history in a relatively short amount of time. So there's some critics of Sigma that say, well, 20 years isn't long enough. And for the people that actually work in the water sector, 20 years is, I don't want to say overly ambitious, but it is ambitious because there's a lot of history involved and a lot of inertia to making this happen. So again, where are we now? So in January, at the end of January, all the critically overdrafted GSPs were due. So there are 21 basins that are identified here in this red area, again, mostly in the southern part of the Central Valley, and then some along the Central Coast. And so of these 21 basins, we had 100% success rate of submitting the GSPs. So these are all currently under review by DWR. You can imagine that these reports are hundreds to thousands of pages long, so it's going to take some time to go through them. But the good news is that every single one of them submitted a GSP, and so that is a success in and of itself. So now we're going to start moving into where do we move forward from here? So we have these GSAs and we're working on these GSPs. So how are we actually going to achieve sustainability? And again, it comes down to this fundamental equation of mass balance, which is our in minus out is our change in storage. And so there's really only two things that we can do on a very macro scale. We can either increase recharge or we can decrease demand. Those are essentially the two ways that we can balance our inputs and our outputs to get this change in storage to be zero on a long-term average. And so everyone would like to increase recharge because nobody wants to decrease demand. The problem is that, unfortunately, decreasing demand is most likely going to be the only way to achieve sustainability in some basins. Because there's some areas where they don't have the water to increase recharge. The basin is already over allocated as it is. And so there's been estimates, one of them is by the Public Policy Institute of California, that approximately about, a little bit over 500,000 acres, or about 836 square miles of agricultural farmland will need to be fallowed. And to put this into perspective, this is approximately 10% of the San Joaquin Valley, or the southern part of the Central Valley. So this is not an insignificant amount of land to be fallowing. So these critically overdrafted basins are going to face significant economic challenges. And with this figure here on the top right, and this is from a very recent paper by a friend of mine at UC Davis, and what they're showing is a sort of a general representation. This line is showing you, again, that storage relationship on the y-axis. And so as this line moves down, we're decreasing our groundwater elevations or our storage, and the x-axis is time. And so from this is, our implementation period, January 1st, 2015, is showing you this minimum threshold, which again is part of our sustainable management criteria. And this is our allowable buffer. And so if we look at how big this allowable buffer is, so if you started off a little bit higher than what your minimum threshold can be, this gives you some flexibility. And so they've run some scenarios, some economic scenarios. And so what the graph here on the left is showing are 3 different curves. On the x-axis is the reduction in water use that they're going to need to do to achieve sustainability. And on the y-axis is the actual probability of achieving sustainability. So 0.5 means there's a 50-50 chance that they're going to achieve sustainability, and 1 is 100% chance of achieving sustainability. And so you can see that with these curves, as this number becomes more negative or your buffer is bigger, you need less reduction of water to achieve the same percentage chance of achieving sustainability. And so you can see that for a 50% chance of achieving sustainability for a 6-meter buffer versus a 0-meter buffer is about 250 million cubic meters of water. So a pretty substantial, reduction in water usage if you're a bit more flexible with your sustainable management criteria, if you have that available to you. And so what this translates to as far as annual economic losses, because again, this farmland is going to be going fallow, so you're losing revenue not only from selling that agricultural product, but also from the farm labor, from any of the ancillary materials that go into farming, so fuel costs, tractors, so on and so forth. There's lots of things that go involved. If anybody is a farmer, you know that there's tons of work involved with farming and lots of people involved in it. And so again, this is showing 2 different plots for Lex Flexible on the left plot here, and a little bit more flexible on the right. And so if you're a little bit more flexible with this minimum threshold, your annual economic losses are probably going to be a little bit less. And also the implementation time is also going to be a factor too. So a 20-year implementation is going to cost you a lot more than say 100 or a 200-year implementation. But 20 years is where Sigma is at, and that's what they're going to be aiming for. And so even though there's going to be significant economic losses for these critically overdrafted basins, really the only advantage that they have is that their problem is much better defined. Because they've been overdrafted for so long, they've essentially stranded their stream connections, and so they don't have these groundwater surface water interactions to deal with. So from an economic perspective, it's not desirable to be there, but from a scientific perspective, for those that are helping develop these GSPs, this groundwater surface water interaction part is the most complicated in my opinion, and I think in a lot of other people's opinions, and the most nebulous. It's very difficult. And so if we look at the 6 undesirable results for Sigma, if you take out the surface water depletion or this groundwater surface water interaction aspect from the GSP, and again, this is because January 1st, 2015, the groundwater was not connected to surface water, so they don't have to worry about that according to Sigma. And so these other things are relatively easy to quantify and develop objectives and thresholds for. So again, lowering of groundwater levels and reduction of storage, it's fairly easy to put concrete numbers on those and where you don't want them to go. Same with seawater intrusion, because those are largely tied to the groundwater levels, and land subsidence is largely tied to groundwater levels as well. And then degraded water quality, we have maximum contamination levels and so on and so forth. So we can actually put numbers on these relatively easily. Groundwater surface water interactions, on the other hand, are more difficult to quantify. They're notoriously difficult to quantify. And so part of this is because exchanges of water between groundwater and surface water are usually pretty diffuse because they're small, but because they occur over a large area or distance, then they add up over a long reach. And so because these are relatively diffuse and relatively small at a single point, there tends to be lots of measurement noise. And so there's a lot of uncertainty with some of these measurements. And these fluxes can be highly heterogeneous. What this plot on the right is showing is on the x-axis is showing time. So if we're moving forward at a single location in time, and on the y-axis, we're moving downstream. So if we took a horizontal slice through this plot, we'd be looking at a single location over time. And if we took a vertical slice, we'd be looking at a single time. So for example, June 5th, 2000, and moving downstream. And what these red and blue colors are showing you is the flux either to or from groundwater to surface water. So the red colors are showing where the stream is losing water to the groundwater, and blue is showing you where the stream is gaining water from the groundwater system. And so these are highly heterogeneous, and this was an output from our Scott Valley model. These white sections right here is actually showing you where the stream has gone dry. This down here on the bottom is this highly altered Yuba dredge tailing section, which goes dry for pretty much every year, and so this is reflected in the model. And again, these fluxes between groundwater and surface water are primarily calculated using these numerical models, and these models have a large amount of uncertainty with them or associated with them. They're not perfect. They're our best tool for evaluating them, but again, they're relatively fuzzy, and so it's hard to get concrete numbers from these. And there are numerous complicating factors for this. And one of them, I like to show this plot because it just shows how variable precipitation in California is. This is the coefficient of variation for precipitation at stations across the US. So this pink color means that there's very little variation from year to year, so they get essentially the same precipitation. There's a little bit more of an increase as you move into the Midwest. And then the Pacific Northwest, pretty similar. It's basically a drizzly climate in Seattle and so on and so forth. And as you get to California, we have these really high coefficient of variations because we either have some years that are very wet and some years that are very dry and very few that are mostly in between. Average precipitation in California on an annual basis is more of a numerical construct than an actual physical reality. And so because of this, there's naturally some streams that went dry, in the historical past, and trying to account for that in our management is difficult to identify because it's hard to hold people accountable to a higher degree than things are naturally, but you also know that there are human impacts that are layered on this, so it's very difficult to suss out. And so the other thing is, and I discussed this before with the groundwater surface water interactions, is that anytime you pump water, you're balancing it by a loss of water somewhere. And so we've known this for a long time. This is from a paper by C.V. Tice in the 1940s. But this stream flow depletion is not constant in time and space. So this plot on the left is showing you is as you pump water from a well, in the early times of pumping, you're mostly getting your water from storage. And as you increase your pumping time, more and more of that water is going to be drawn from either stream flow depletion if there's a stream nearby or increasing recharge from somewhere else. So you're decreasing the water that's coming from storage and you're increasing the amount of water that's coming from another source. And so what this plot is showing you on the right-hand side is just a graphical representation where as you pump more of this water, this is this cone of depression that I mentioned before that occurs near the well. And so in early times, there's still water that is discharging to the stream. As this cone of depression gets larger and larger, you reverse this gradient and water is now coming, instead of moving from the aquifer to the stream like it was before, it's now moving from the stream into the aquifer. And so, like I said before, these stream flow depletion effects can vary in time and space. And so on the top plot here in box A is just showing you this the seasonal pumping. So this is just showing you somebody turns on a pump and it's on for essentially the entire growing season and then they turn it off. So it's a crude representation of what happens, but it's a decent example of what's happening. And on these lower three, so B, C, and D are showing you the stream flow depletion in the pink line. And then this is the black line is sort of the long-term average. As you move away from the stream. So this is a well located at 300 feet, C is a well located at 1,000 feet, and D is a well located at 3,000 feet. So you see these more acute, sharper impacts from wells that are located near the stream, and this more diffuse, sort of even, slow sucking of water from the stream as the well moves further back. So the corollary to this is so it takes, for example, in this example, about 7 years to reach this sort of, steady state scenario. That also means that after you turn off the well, it's going to take 7 years for that to go back and recover where it was. So these impacts can be fairly long lasting, and it's highly dependent on where the well is located. And again, yeah, sorry, I should have shown this before, but on the x-axis is time, and this is distance from the stream where the well is located. And some of my research has shown that this is complicated even further, where if you have streams that go dry, you can switch back and start drawing from that storage reservoir, and you can complicate this even further by not having these nice constant relationships where you switch back and you actually stop your stream flow depletion because the stream has disconnected at a certain gauge. But then once that stream gets reconnected, you now have even greater stream flow depletion impacts at a much shorter amount of time. You're essentially focusing those stream flow depletion impacts that would have occurred, say, over 3 months, and focusing them into maybe 2 weeks. And so this complicates things even further. And this is a paper that we're currently writing and looking to submit in the next couple of months. And so this is why these sustainable management criteria for surface water depletions are very challenging to come up with, because the measurable objective is very hard to measure. It's hard to put a number on how much water is actually, moving into or out of the stream from the aquifer. And the second thing is the minimum threshold is, remember, it's significant and unreasonable. And so how much is unreasonable to deplete surface water? Because anytime you pump groundwater, you're going to be taking from surface water. But how much of that is unreasonable is difficult to quantify. And I'm not a fisheries biologist or anything like that, but I have never really come across somebody that can give me a hard concrete number saying exactly how much CFS and where fish would need this water. They can identify areas where it's important, but the hard and fast numbers are much more difficult to come by. And so I'd like to just end on this by saying that working towards sustainability in these basins is going to require a lot of work, and it's going to require consensus building and compromise and adaptive management, and above all, trust. In my opinion and in my experience, the basins that are going to have the best experience and most likely achieve sustainability are the ones that come together and face these difficult decisions head on, and hopefully don't resort to just trying to sue each other over this. So that's my goal. Like I said, we are currently right in the middle of all of this, so history will be the judge of how well we actually achieve this, but I am optimistic. There's some references if anybody is interested, and with that, I'd be happy to take any questions.
I'm also going to check on to the live Facebook to make sure that if anyone had any questions there as well.
Perfect.
Every time I did have a question, you ended up answering it like 2 minutes later.
Oh, that's good to hear. I always get nervous when there's no questions because I either did a fantastic job or I thoroughly confused everyone.
Okay, it's looking like no one on Facebook has any questions either. And I'm going to double check with the rest of the participants to see if they had any other questions or had any questions. Okay, everyone just saying thank you. Okay. It's looking like there are no questions out there. So I appreciate you taking the time to give a presentation. I thought of
no problem. Yeah, if anybody ends up thinking of a question later on, my contact information is on here. Feel free to shoot me an email or give me a call.
Okay. It looks like someone did have a question. Not sure if you covered how this could affect the value of the land or the population movement.
Specifically Central Valley. So yeah, I mean, obviously, land that doesn't have water rights associated with it is in the Central Valley is essentially worthless. That being said, groundwater rights are considered correlative, and so that's why these sustainability plans are taking into account all these various stakeholders. So generally, if there's going to be reductions, either it will probably be across the board, or more likely, what will happen is people will probably be bought out. That's going to be my assumption. It's really hard to say, and it's really dependent on the localities. But again, there's going to have to be some reductions, especially in the southern part of the Central Valley, unless they can find other sources of water to import. And unfortunately, most of that water is already spoken for. So it's going to be difficult. But yeah, not having water rights is definitely going to affect the value of the land, and it can affect local economies too. I mean, this is a significant challenge that we're going to be facing. It's not going to be easy. And as far as population movement, yeah, I mean, you may see, you know, some of these smaller areas, you know, drying up if agriculture is their, you know, only source of income, and that's no longer available. That being said, I'm not a social scientist, so I'm a poor person to ask about that.
Okay, looks like there's no other questions. So thank you for giving a presentation today. And if anyone does have any other questions, I'll go ahead and give them your contact information as well.
Perfect. Well, thank you very much, everyone. Have a great day.
You too. Thank you.